In this video, we will study the differential equations and solutions of 1, 2 and 3 dimensional waves. Also, there is an essay where we derive an expression for the fundamental frequency of transverse vibrations in a stretched string. Differential equation of a one-dimensional wave is given as dou square psi by dou x square is equal to 1 by v square into dou square psi by dou t square. Here, the Greek alphabet psi, it represents the wave function, whereas small v, it represents the wave velocity. Wave function psi is the physical quantity that changes in a wave. Consider the case of a one-dimensional wave, for example, transverse vibrations in a stretched string on plucking it. Here, x represents the displacement of the particles of the string from the mean position, and since the displacements are perpendicular to the direction of propagation, the vibrations are transverse and we get a transverse wave. Here, the physical quantity that is varying with time is actually the height of the string x from the mean position. So we can say that the wave function psi in the case of a one-dimensional wave is a function of x and t. That is a function of position coordinate x and time t. When we consider the case of a two-dimensional wave, for example, ripples formed on the surface of a pond, there the physical quantity that is varying with time is actually the height of the water, and the variations take place in a plane. So we say that for a two-dimensional wave, the wave function psi is a function of position coordinates x and y and time t. So the wave function psi depends on three variables x, y and t, whereas in the one-dimensional case, psi depended on x and t only. Now coming to the three-dimensional case, for example, sound waves, the physical quantity that is varying with time is the pressure of the gas, whereas in light waves, the physical quantity that is varying with time is the intensity of electric and magnetic fields. Please note that the pressure variations of gas in the case of sound waves and intensity variations of electric and magnetic fields in the case of light waves happen in all directions. So, in the case of a three-dimensional wave, the wave function psi is a function of position coordinates x, y and z and time t. So remember the points. Wave function psi is a physical quantity that changes in a wave, and in the case of a one-dimensional wave, it depends on the variables x and t, and for two-dimensional case, it is a function of x, y and t, whereas in three-dimensional case, it is a function of x, y, z and t. The term wave function was actually coined in quantum mechanics in connection with matter waves. We will study more about wave function in quantum mechanics module 3. It is a very important short question often asked for university exam. As of now, you just remember that whatever wave we take, some physical quantity is varying, and variations of that physical quantity make up that wave. And this physical quantity we call as wave function. Now coming back to the differential equation of a one-dimensional wave given by dou square psi by dou x square is equal to 1 by v squared into dou square psi by dou t square. Here, now you know that since this is a one-dimensional case, we have only the variables x and t, that is the position coordinate x and time t. Psi is the wave function and v is the velocity of the wave. Now one more thing that I want to add here is that we have used two second order partial differential operators, dou square by dou x square in the left hand side and dou square by dou t square in the right hand side. So my question is, why didn't we use d square by dx square in place of dou square by dou x square, and also why didn't we use d square by dt square in place of dou square by dou t square. The answer is we use partial differential operators when the function depends on two or more variables. Here, the wave function psi in one-dimensional case is a function of x and t. That is, it depends on two variables. That is why we are using partial differential operators on both sides. For a two-dimensional wave, we have to add a term in the left-hand side showing the variation of psi in the y direction also. So, the differential equation of a two-dimensional wave becomes dou square psi by dou x square plus dou square psi by dou y square is equal to 1 by v square into dou square psi by dou t square. For a three-dimensional wave, we have three terms in the left-hand side showing the variations of psi along the x, y and z directions. So the differential equation of a three-dimensional wave is given as dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square is equal to 1 by v square into dou square psi by dou t square. Now we will see an operator called del. The significance of this operator del is that it is a vector partial differential operator. It is defined as I into dou by dou x plus j into dou by dou y plus k into dou by dou z, where I, j and k are unit vectors along the x, y and z axis. Now, if you take the dot product of del, that is del dot del, you will get del square and it is defined as dou square by dou x square plus dou square by dou y square plus dou square by dou z square. This new operator del square is called the Laplacian operator and it is a scalar operator unlike the operator del. You will study about this operator del more in your maths classes. Differential equation of a three-dimensional wave can be represented in a more concise form if we use the Laplacian operator del square. That is, if you take psi as common factor from the left-hand side of the equation, you can write it as del square psi is equal to 1 by v square into dou square psi by dou t square. So these are the differential equations of 1, 2 and 3-dimensional waves. Solution to a one-dimensional wave equation is represented as psi is equal to a sine kx plus or minus omega t. Here k is our wave vector whose magnitude is k is equal to 2 pi by lambda. K is also called propagation constant. Omega is the angular frequency of the wave and A is its amplitude. Psi is equal to A sine kx plus omega t represents a wave propagating in the negative x direction, whereas psi is equal to A sine kx minus omega t, it represents a wave propagating in the positive x direction. Instead of using sine function, we can also use cos. That is, psi is equal to a cos kx plus or minus omega t. Another way of representing the solution is psi is equal to a into e raised to I kx plus or minus omega t. You must have studied in your maths classes that e raised to ix is equal to cos x plus I sin x. Since e raised to ix has both sine and cosine function, we can represent the plane wave solution of a one-dimensional wave as psi is equal to a into e raised to I kx plus or minus omega t. Please remember this solution because we will be using it in quantum mechanics module 3. In the previous slide, we have seen different ways of representing solution to a one-dimensional wave. Now we will see the solution of a two-dimensional wave. For a one-dimensional wave, the solution was psi is equal to a sine kx plus or minus omega t. When we come to the two-dimensional case, we can write the wave vector k as k is equal to ikx plus jky, where I and j are unit vectors along the x and y directions. That is, wave vector k has components kx and ky along the x and y directions respectively. So, here the solution can be written as psi is equal to a sine kx into x plus ky into y plus or minus omega t. In the three-dimensional case, the wave vector k has three components kx, ky and kz along the three directions x, y and z respectively. So the solution can be written as psi is equal to a sine kx into x plus ky into y plus kz into z plus or minus omega t. Solution of a three-dimensional wave can be further simplified using the position vector which you have studied in your maths classes. The position vector r is equal to xi plus yj plus zk. When you take the dot product of wave vector k and position vector r, that is k dot r, you will get kx into x plus ky into y plus kz into z. Now, the solution becomes psi is equal to a sine k dot r plus or minus omega t. Instead of psi is equal to a sine k dot r plus or minus omega t, we can also represent the solution of a three-dimensional wave as psi is equal to a cos k dot r plus or minus omega t, or as psi is equal to a into e raised to I k dot r plus or minus omega t. So these are the solutions of 1, 2 and 3-dimensional waves. Now next is an essay where we derive an expression for the fundamental frequency of transverse vibrations in a stretched string. Now before going to the essay, you are supposed to know certain things, like if t is a vector which subtends an angle theta with the horizontal. Now you can give the horizontal component of this vector t as t cos theta and the vertical component as t sin theta. Now, if the vector t subtends an angle theta with the negative x-axis, the vertical component t sin theta and the horizontal component t cos theta can be resolved as shown here. Again, this you must have studied in your +2 classes, that the slope of the curve gives tan theta is equal to dy by dx. You know that tan theta is equal to sin theta by cos theta. When theta is very small, cos theta tends to 1, and therefore you can write tan theta is approximately equal to sin theta when theta is very small. Transverse vibrations in a stretched string. First point is, consider a long uniform stretched string which is under a tension T. Now when you pluck the string at a point, a pulse is produced which travels along the string. Now as the third point, you have to say that this pulse is transverse in nature. That is, since the displacement of the particles of the string are perpendicular to the direction of propagation, the wave is transverse in nature. Hope you remember, I had earlier mentioned in the video that wave function is a physical quantity that changes in a wave. Here, the physical quantity that is varying with time is the displacement of the particle from the mean position. Usually, we denote the displacement as y in the case of a string. But here, instead of y, we can also use the general term wave function psi, which is defined as the physical quantity that varies in a wave with time. In the second part of the essay, we have to describe the figure. The figure gives a snapshot of the transverse pulse at any given instant of time. Here, y-axis represents the displacement of the particle from the mean position, But instead of y, here we have given the wave function psi, which represents the physical quantity that changes in a wave, and in this case it is the displacement of the particle from the main position. So in the second part of the essay, you have to include 4 points. First point is, consider two neighboring points P1 and P2 separated by a small distance delta x. Here P1 is at a distance x from the origin and P2 is at the distance x plus delta x from the origin. So the length of the small element P1, P2 will be delta x. At points P1 and P2, they have drawn tangents which give the direction of the tension at points P1 and P2. Second and third points are related to tension. The tension is uniform throughout the string. Also, at any 2 points on the string, the tensions are directed oppositely. Please note that at points P1 and P2, only the vertical components of tension are given. At P1, the vertical component of tension T sin theta 1 is directed downwards. At P2, the vertical component of tension T sin theta 2 is directed upwards. They haven't shown the horizontal components of tension, namely T cos theta 1 at P1 and T cos theta 2 at P2. Can you say why they haven't shown the horizontal components of tension? The answer is the horizontal components of tension, they don't have any role or they don't play any role in changing the displacement of the string. That's why they haven't shown in the diagram. So the fourth point is the vertical components of tension are T sin theta 1 and T sin theta 2, where theta 1 and theta 2 are the angles made by tangents at P1 and P2 with the horizontal direction. Now we come to the third part of the essay. Consider the small element P1, P2 of length delta x. At P1, the vertical component of tension T sin theta 1 is directed downwards, whereas the vertical component of tension at P2, which is T sin theta 2, is directed upwards. So, the resultant vertical force acting on the small element P1, P2 is given by upward force minus downward force. It is usually taken conventionally as upward minus downward. So, it will be T sin theta 2 minus T sin theta 1. The resultant vertical force acting on the small element P1, P2 is F is equal to T sin theta 2 minus T sin theta 1. Here please note that you shouldn't write T2 sin theta 2 minus T1 sin theta 1 because the tension is uniform throughout the string and there is no T1 and T2, only T. Since theta 1 and theta 2 are very small, sin theta 2 and sin theta 1 are also very small. So it means sin theta 1 is approximately equal to tan theta 1 and sin theta 2 is approximately equal to tan theta 2. Therefore, the equation becomes F is equal to T into tan theta 2 minus tan theta 1. Here they have taken the tension T as the common factor. Slope of a curve is given by tan theta is equal to dy by dx. But in our case, y coordinate is psi, the wave function. Therefore, tan theta is equal to d psi by dx. But again, a wave function psi, which we take as the displacement of the string, is a function of position x and time t. Therefore, you have to use partial differential operator. That is, tan theta is equal to dou psi by dou x. Tan theta 1 is the slope of the curve at point P1, which is at a distance x from the origin. Therefore, tan theta 1 is written as dou psi by dou x at x, whereas tan theta 2 is the slope of the curve at point P2, which is at a distance x plus delta x from the origin. Therefore, tan theta 2 is equal to dou psi by dou x at x plus delta x. Earlier we had written f is equal to t into tan theta 2 minus tan theta 1. Now it can be rewritten as f is equal to t into dou psi by dou x at x plus delta x minus dou psi by dou x at x. Put this as equation number 1. Now we are going to change the left hand side of the equation, that is F. Now what is F? F is the resultant vertical force acting on the small element P1, P2 of length delta x. If m is the mass per unit length of the string, what will be the mass of element P1, P2 whose length is delta x? It will be m into delta x. Now, the acceleration is usually given by d squared x by dt square or d square y by dt square. In our case, y is wave function psi. So we have to write d square psi by dt square. Again, since psi depends on x and t, you have to use the partial differential operators. That is, for acceleration, we have to write dou square psi by dou t square instead of d square psi by dt square. Therefore, the resultant vertical force F acting on the small element P1, P2 of length delta x can be given as the product of mass and acceleration. That is the mass of the string, which is m into delta x, and its acceleration dou square psi by dou t square. Now substitute the value of F in equation number 1. Then it becomes like this. By cross multiplying, bring the tension in the right hand side to the left hand side of the equation and delta x from the left hand side to the right hand side of the equation. Now you will get equation number 2. You must be familiar with this equation which you have studied in your maths class during plus 2. It gives a definition of differentiation. You can see that the right hand side of equation 2 is similar to the left hand side of this equation. In place of dou psi by dou x at x plus delta x, you have f of x plus delta x, and instead of dou psi by dou x at x, we have f of x. So, the right hand side of equation 2 can be written as f dash x. That is, instead of f dash x, we can write dou square psi by dou x square, and it happens only when the delta x tends to 0. So, as delta x tends to 0, the right hand side of equation 2, it becomes dou square psi by dou x square. And dou square psi by dou x square, it represents the rate of change of dou psi by dou x with respect to x. Now we get the equation 3, which is m by t into dou square psi by dou t square is equal to dou square psi by dou x square. You can see that equation 3 is similar to the differential equation of a one-dimensional wave. So on comparing the two equations, we can write m by t is equal to 1 by v square. So from this equation, we get the velocity of the wave v as is equal to root of t by m, where t is the tension in the string and m is the mass per unit length of the string. You must be familiar with these figures. The first one shows the fundamental frequency or first harmonic. The second one, it shows the second harmonic, and then the third harmonic. Capital A and capital N denotes the antinodes and nodes. In our essay, we have to find the fundamental frequency of transverse vibrations. So you have to take the first figure. So we are going to find the fundamental frequency of vibration. For that, we have already got an expression for the velocity of the wave, which is v is equal to root of t by m. Now, if L is the length of the vibrating segment, then it is obvious from the figure that L is equal to lambda by 2, or lambda is equal to 2L. Velocity of a wave is given by v is equal to n lambda, where n is the frequency and lambda is the wavelength of the wave. Now instead of n, small n, we can use nu or small f for frequency. But here we have used small n. V is equal to n lambda. We have already got an expression for velocity v as equal to root of t by m and lambda as equal to 2l. Now substituting the values of v and lambda on this equation and on rearranging, you will get the frequency as n is equal to 1 by 2l into root of t by m. So, expression for the fundamental frequency of transverse vibrations in a stretched string is given by n is equal to 1 by 2l into root of t by m, where L is the length of the string, T is the tension in the string, and m is the mass per unit length of the string.